Hello everyone and welcome back to another video. So today we're going to be talking about open the lock. It is the fourth problem in the week 1 of the June Leak Coding Challenge. I didn't do this during the day, but uh, I just solved it today. It took me like I'd say like 20 minutes. So yeah, I'm here to share the solution I came up with you guys. So in this problem, you have like a lock and it has 4 circular wheels, so it's like one of those turny locks, I guess, like a kind of like a bike lock, and you can spin each wheel to a different number and it wraps around. So yeah, I have a bike lock that does this, so that's what I immediately think of. And uh, yeah, you can just rotate these wheels to go through all these numbers, right? And the lock initially starts at 0, 0, 0, 0. So all the numbers will be zeros. And you're you're given a list of strings, and these strings here represent states that essentially, if the lock ends up in that state, you won't be able to unlock the lock. And so you're given a target, which is the arrangement that you're trying to get the lock into, and you're supposed to return the minimum number of turns required to open the lock. So to change this 0, 0, 0, 0 from from this to whatever the target is. And if you happen to step across a dead end, then the lock will just be locked and it'll be impossible to move. And so they kind of give an example here. So you could turn the 0 here to turn it into a 1, and then get these the second and the fourth number to a 2, and then turn this back to a 1 to reach the target. And it's important not to go right away, because let's just say you change this to like 2 and then you try to change this to a 2, you would end up in a dead end, right? So that'd actually be impossible. And so this would be the right sequence, and the length of the sequence is 6, so that's what you're supposed to output. And if you cannot reach the target, if wherever you try to go you end up in a dead end, so like sort of the dead ends kind of trap your ability to turn and get out of it, then you're supposed to just output -1. So this problem was a little tricky to think about where to start, but a useful thing to look at is actually the constraints. So let me just make this a little bigger, to be honest. So yeah, a useful thing to look at is actually the constraints. Let's do this. So we know that the target length is going to be 4, right? So because there's only 4 of these circular spinny wheels, and each wheel only has 10 slots, right? So kind of at most there's like 10 to the 4 like kind of permutations. So this kind of signifies to me that a kind of brute force searching approach would actually work here, because if you think about like BFS or something, you'd only have to go through 10 to the 4 like possibilities at most to try and work your way toward the final target. And so with that in mind, then it's really easy to start thinking about the solution. And yeah, so I'll start talking about the solution. So let me just get rid of that. So if we imagine the starting lock position as like 0, 0, 0, 0, then we can kind of treat this as like a I don't know if it's actually like a graph type of, it's like a similar idea. We're essentially going to use BFS to search out into different other possible states that this lock can be. So what we can do is we can say like, oh, of course this state, it'll connect to like the state where you increment just this 1, and this will the states it connects to are just the states that you can reach after turning any lock once. So it'll also be connected to, of course, 9000, because you could just turn it the other way and it'll wrap around into a 9, right? So it's just exactly like those like combination spinny locks. And then so another one it could be at is if you increment the second number to like a 1, same with that. So then these are all the reachable positions. Like there's some obviously some other ones where you increment the third and the fourth, and you can do one rotation forward or one rotation backward, and backward after 0 wrap around to 9. So this layer would represent all of the states reachable after one turn. And yeah, so since you're supposed to return the minimum number of turns it takes to reach the target, because each move consists of turning one wheel, one slot. So this also is incredibly useful to us because, like, hey, these are all the positions you can reach after just turning one wheel, one slot. And then after that, you can go on each of these states and do the same thing for each of these states. And then you have an even bigger thing with a lot of values in it. And uh, then we'll be able to find all the things reachable after like two turns, right? So one possibility could stem from this, and this could be like a 2, and then zeros following it, and that just represents on the first turn you turn this once, on the second turn you turn this once, right? Like in the same direction again. And yeah, so you can just grow this kind of tree of possibilities, and at every next layer, that's how many turns it'll take to get to that layer. And um, yeah, so then you can kind of just search out into all the different possibilities, right? And uh, the conditions where we don't want to add this state to like a queue of states to search, because we're essentially trying to use BFS here, right? We're going layer by layer and filling in all these possible states. And whenever we find that we reached a state that's equal to the target, like eventually we'll find, what was it, the input like 0202, we'll eventually find that we, through some path of turns, we can reach this, and then we want to return whatever this depth of like search we have, right? Whatever layer this is. And so we'll have like a queue of uh, like um, states that we need to check from. And so we can start by feeding this into the queue, and then we can, while this queue has states to check, we can grab the state, manipulate it to find all of these different possibilities. And if the possibility is not a dead end, we want to add it into the queue. So let's just say, for example, 1000 in this hypothetical example. If this was a dead end, we wouldn't want to add this into the queue, because if we visit it, it's just not going to be, we're not going to be able to get anywhere, right? Because if you reach a dead end in one of these things, then the wheels of the lock will stop turning and you will be unable to open it. And since we're looking to open it, there's no point to explore anywhere down this path because we'll just reach a dead end. And then we can just add the possibilities that do work into our queue. Then we can just work through those, pop those off, add more possibilities, and yeah, sort of this kind of BFS style idea. And so now that we know the kind of the theory behind the problem, uh, let's go into how to actually implement this. So the first thing to notice is when you want to check, because when we add things into the queue, right? When we add things into the queue, we want to only add them into the queue if they are not a dead end. So if they are not a dead end, not dead end. So if it's not a dead end, we want to add it to the queue as a state that we want to potentially explore. So we need to be able to check if it's a dead end really quickly. So we can just have a set of strings and add all of our strings in this array into this hash set to make lookup really fast. So now whenever we permute one of these, calculate one of these new states that we can get the lock into after one turn, we can instantly know if we should put it into our queue or not. And here we just do some checks because without these checks, you kind of fail some edge cases inside the problem. And so these are just pretty trivial. So if a dead end is the initial combination, then it's obviously unsolvable, right? Because if you look at the constraint, target will not be in the list dead ends. So if the dead ends contains this starting thing, you know the target's going to be different from it. But since you know the starting thing is all zeros, you start at a dead end, so you just can't open the lock. So you return -1 in that case. And here, if your target is obviously the starting position, you just return 0 because it'll take you 0 turns to unlock the lock. The lock would just be already unlocked. So after these two trivial checks, we can go on to the actual algorithm. So we can maintain a map, and this map will keep track of a possible code, so the state of the lock, and how many moves it will take to reach that state. And we will have a queue, and this will represent the lock states that we need to explore. And I made a custom class for this. It might not be needed, but this class lock state will just hold in it a state of the lock and the number of moves it'll take to reach that state. So we can add our starting lock state, because it'll take us 0 turns to reach this state, into the list of states that we want to explore. And while there are states to explore, we can just pull one from the front of the queue and then add it into our map here, because yeah, this map will just help us keep track of what states that we've seen so far. Because if we turn a lock like a little wheel, like clockwise, I guess, and then turn it back, we don't really want to turn it back, because then that's just undoing what we did. So we want to keep track of all the states that we have seen so far. And actually, looking at this right now, we don't even need to use a map here. I think we can just use a set of strings, because I never get anything from the map. Oh, okay, that's kind of dumb. But anyway, so the key of this map will just be the state of the lock that it's in, right? So we just want to put that in, and then we want to basically, this here, what this for loop does is it essentially calculates all the possible states that the lock can be in after one turn of one wheel. And so this for loop will go from 0 to 3, and every single time I'm basically pretending that I turn the ith wheel, right? So what we can do is we can these function here, this will essentially take in a state and an index and rotate it in like a forward direction, and then this will do the same but in the other direction, right? So if we look at these functions here, we have a string. This is the state of our lock. This is the index of the wheel we want to turn. We can grab the number at that index just by taking the character, subtracting this ASCII value of 0 from it, and then we can add 1 to it. So this is like incrementing it forward 1, and then modulus it by 10 because we want it to wrap around, right? So like for all numbers other than 9, like it'll go from like 8 will go to 9, and like 1 to 2, etc. But from 9, if we move it forward, we want it to go to 0. So 9 plus 1, we modulus that by 10, that'll equal 0. So this kind of just implements our wraparound. Then what we want to do is we want to just take the substring from our original string from 0 up to that index, and this obviously doesn't include the index. And then we want to add the new value of that wheel we returned, because that's the value of the wheel at that index now, and then just substring from, take the rest of the string after the index. And so this will return a new string that basically represents the state of the lock if we rotated it one of the wheels. So for example, if we have a state like 0, 0, 0, 0, and we called this on like index 2 and increment, it would look at this wheel, because that's index 2, right? And it would rotate it, and it would return a string like 0, 0, 1, 0. And that's exactly what this does, and this just decrements it. So it's the same logic, but instead of incrementing it by adding 1, we just subtract 1, and this is just a little shortcut for saying if our number is 0, we want to wrap around to 9. And so this will make it so, let's just say we want to rotate this wheel again. If we want to decrement it the other way, it'll become this, and this is a state that we can reach from turning the wheel, right? And so then for each of these wheels, I will calculate the states if I can rotate it forward and backward here. And if this new state is the target state I'm looking for, then I'll simply return the amount of moves it took to get to this state, add 1 to it, right? Because this rotation is that one extra rotation that we did. Because if you remember this lock state here, C, it'll hold the state of the lock and the number of moves it took to get to it. So if we just pull the lock state from our queue of lock states to explore, we can just find out how many moves it took to get to that, and then add 1 to it. And otherwise, if it's not a dead end and we have not seen it yet, so it's a new lock position, then we'll just add that to the list of possible lock positions, like our map here, and we will add that to our queue, which keep tracks of the lock states that we need to explore, right, by using this. And this is the state that we calculated, and this is obviously adding a move to the amount of moves it took to get to this state. And we can use the same exact logic for like rotating the wheel the other direction. So this is another state that you can turn it into if you turn the wheel the other direction. And so this will essentially search out and find all the possibilities that you can reach. So while there are things to explore, it'll just keep on feeding into the cycle and finding all those new layers of states to explore, right? And so if in one of these ways to rotate the lock, we find the target, then obviously we can just return the answer. And if we come out of this while loop and then we know, hey, I've explored everything, there's no sequence of moves that can solve the lock, we can return -1 in this case. And the last thing to explain here is the reason why we can simply add 1 to the amount of moves it took to this state is because we're not using like DFS here, we're using BFS. So we're first finding all the states that can be accessible using 1 turn, and then adding them into the queue here, right? And then we'll have like a group of items after 2 turns. So when we see this position and we can find a new position, we know that that new position cannot be reachable in fewer than like 2 turns. So we can just say 2 turns plus 1. That's 3 turns to reach this new position here. So that's why we can just directly add 1, since we're doing this with a queue type of exploration instead of straight up DFS. So yeah, and this will work and solve the problem. And so kind of already did some runtime analysis on this, but uh, since at most you'll need to explore 10 to the power of 4 states, because there are 4 different wheels, each with 10 different values it can be. There are 10 to the 4 combinations, so that's just uh, that's like that runtime will not TLE, and you'll be able to solve the problem using this approach. So that's it for this video. I hope you guys enjoyed it. Thank you guys very much for watching, and I'll see you guys later.